This is not drawn very good, but it's okay. This is the circuit that I had wired up. That it's been up here for a while. I just figured out how to rewire it. I need to re-label some of my wires. But what we have here, this is our error amplifier. This is our set point. So this is basically the way most closed loop system works. This is our feedback. Of course, this is a motor. And then this means it's mechanically connected to the potentiometer. So this is our sensor. This is our position sensor. This is a symbol for what we call an NPN transistor. So this guy here turns on when this lead right here is positive. It turns on off when it's negative. This is a PNP transistor, and it turns on when this lead right here is negative. So depending on which one I turn on, I can change the polarity going to the motor. So if the top one turns on, I put a positive on the motor, and it turns in one direction. If this guy turns on, it puts a negative on the motor, and positive. The op amp, or the operational amplifier, the error amplifier, cannot provide enough current to drive the motor. It's not designed to drive the motor. What it's doing is designed to give us an indication of when the two inputs are equal. If the two inputs are not equal, then it saturates in the direction of which one's greater. Now, in closed loop systems, the feedback is what we call, it has to be what we call, we have to use what we call negative feedback. An example means if positive feedback means if your car is going too fast, it would make it go faster. Negative feedback means if your car tries to go fast, the feedback makes it go slower. So that's why this is coming into the negative. This is coming to the positive. So this is negative feedback. If I swap this around, I'd be doing positive feedback into that problem. So closed loop systems use negative feedback. So what happens, I come over here and I turn my set point, I put a voltage into this. This compares it against this voltage there. Right? Understand? That makes sense? If they're not equal, the motor turns on in one direction, depending on which way it's off. When they are equal, this right here should go to zero. The motor should maintain that position. The problem is, and we'll talk about this later on, we're using what we call proportional feedback. The problem with proportional feedback or proportional system is they have a tendency to oscillate. Why do they oscillate? Well, we turn the motor on, the motor starts spinning. The motor can't stop. It's got inertia. So it goes past. When it goes past, it says, okay, you passed. And what does it do? Turns on the other direction. Motor comes up, it's got inertia, goes the other direction. So the problem with proportional controls is they have a tendency to oscillate. You'll see that here. So y'all come over here and look at this. I've got it recorded. But it won't show up too well on the camera. Plus my pod is. So it's a very, very fundamental thing. So here's my shaft. Then I've got it because the shafts are not the same. I've got it taped to my pod. But watch this. I'm going to come over here and take my reference pod and just turn it and look what happens. You see what's happening? Now it's oscillating because it's proportional control. We can probably make it stop if we slow it. And plus it's using tape as a coupling. So as soon as I get an error in my error amplifier, it decides which direction it needs to turn the motor. And it turns the motor until the output of this pot matches what? The output of that pot. So this is a closed loop system, guys. Using a pod as position control. And here's the error amplifier. Here's my two transistors right here. They get kind of warm. But these are the two transistors right here. I didn't draw the resistor. But one of them's an NPN, one of them's a PNP. The NPN controls the positive, and then the PNP controls the negative. On leads. On a sinking and a sourcing sensor is the way they hook it. So an NPN transistor is a seeking transistor, and a PNP is a sourcing. We can show you how those work. Are we okay? Ain't that neat? Anybody want to turn the pop?
Is it on?
Yeah. So what we're doing is we're putting an error into an error amplifier, right? And then with a pot, and then this right here turns to cancel the error out, right? And that's the way feedback works. It's oscillating for two things. This is a very poor coupling. It's only K. And plus it's probably called proportional. It's a proportional control. And later on we'll look at what we call a PI control, which basically with a limit. So a P controller has a tendency to oscillate because of inertia of the devices, especially in motor circuits, because a lot of things when they move and they have inertia, and you're saying stop and they can't do stop, and they overshoot. Then when they overshoot, you got an error. And then it says, okay, we need to go back in the back direction. Turns it on, does what? Overshoot. What we like to do is when it starts approaching it, instead of just going wop, 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 which is what we're doing with proportional control, is to level it off. And the closer it gets to the set point, we do what? We start leveling off. And instead of coming in like this, we come in like this, which gives us a lot better control of it. And those are called I controllers, the PI. So we combine them. A PI controller, we combine them and we could get rid of that. But we'd have to add a little more stuff. We'd have to add an integrator to it. Are you okay?
Yeah. On the PNP and NPN, you're not set up a single source.
No, these are set up. The PNP turns on with a positive and the NPN turns on with a negative. Yeah, it's according to how we hook the loads. So on a PNP sensor, what they would do is they would let me get rid of this. So on a PNP sensor, what we do is we have the PNP transistor connected right here, and then this, which is the N, is connected to circuit common, and then what we do is we put our load up here. So this is where your PLC input would be right there. So if this provides the ground, then we have to put that to a positive, right? Understand? Now an NPN sensor, what they do is they point this guy here is pointed toward the negative DC, and then my load is connected right here. So when we put a 0 right there, this guy here turns on. But over here, since this guy here is providing the negative, then this guy right here has got to provide the what? Positive. So that's why PNP is so in sensors, and we get the voltage gain out of the collector. So notice on both of these, the load is hooked in the collector. And they're not running off a negative positive supply, they're running off a power supply. Make sense? So this would be an NPN, this would be a PNP sensor. It's a sinking sensor. So your load, your PLC would be hooked to plus or whatever. I'm sorry, this is a sourcing sensor. This guy here would do that. And that's just the output of the sensor. That makes sense?
Yeah.
So when we do it to control the motor, control the DC motor, what we have to do is we have to control the current flow through the motor. We have to reverse the current flow through the motor. We can do it by switching it between a negative and a positive polarity, which is what I'm doing here, or we can do it by electrically, mechanically rewiring the motor. Well, we control the current, but the rotor's got so much resistance. So what we're doing is we're controlling the magnetic field. But to control the magnetic field, we need current, but we can't have current without what? Voltage. So yeah. So we control the speed with a voltage, even though the voltage is controlling a current, right? So what I'm doing over there is I'm controlling it, the direction of the DC motor by changing the polarity of the current. The other method that we would see, that y'all would do in motor controllers, if y'all remember the reversing controllers in motor controls, what we did is we controlled it in an H control, what a lot of people call an H controller. This is pretty standard to control it with relays. And this would be forward, and this would be forward. And then this right here would be reverse, and this would be reverse. And your motor, your DC motor armature is right here in the center. And if this is minus and this is plus, if we can code reverse, then the current flow is in this direction, right, for reverse. If we go to forward, then the current flow is in this direction for forward. So this is called an H control, which you're going to see used a lot in DC motor. So do what? Reverse the direction. Because probably 90% of the time, we're not going to have a minus and a plus supply available to it. We'll have one power supply, right? Understand that? An H control. You can see why it's called an H control, because it looks like a what? It looks like an H. So if you ever hear the word H control, then that's exactly. We can do this with solid state devices too. But we would reverse the transistors. Be on each side. This is done with relays. And what we do here is the polarity of the source never changes. But what we're doing is we're either mechanically routing the current, or we could do it through transistors too. So I could come over here and do this like this, right? So you can buy H controls that are solid state. And it would be like this, but it would be these transistors, usually NPN. You can buy solid state H controllers, and they'll be wired like this. And then you'll have a connection where you'd hook your motor right here, right? And then this would be controlled by electronics. So we would turn this guy here on and this guy here on. And the current would flow what? This direction. And then these two other guys would be off. And then I would turn this on and turn this one on. And the current flow would the other direction. So you can buy a solid state H controller, which is basically transparent to you. You have a switch on the outside that says forward and reverse. You hook up two wires that says forward and reverse, and the electronics inside the thing does everything else. Now, what's the advantage of electronics using this? A lot quicker. And plus, you're only dealing with electronics. You've got electrical. Plus this, we can't use pulse width modulation to control the speed of the motor. This right here, not only could we change the direction, we could also change the speed using what we call pulse width modulation. You understand pulse width modulation? What we can do to a DC motor is instead of sending it DC, we can send it pulses. Now notice on these, I'm going to make the pulses at exactly the same frequency, but I'm making them bigger. Now if I pulse the DC motor with this, which one will run faster? This guy's going to run faster. This guy will run slower. So the narrower I make the pulses, the motor slows down. The wider I make the pulses, motor speeds up. This is called pulse width modulation. So what we're not doing is we're not changing the frequency. And a lot of times the frequency would be above the human ear. Sometimes it's not, and you hear these things sing at you. Because you're hearing the windings on the motor pulsing. But what we do is, they call it a duty cycle. The duty cycle is the percent of the period. So the period is the time for one cycle, right? Everybody understand that? The duty cycle would be the percent of the period. So you can calculate the average voltage. You just take the maximum voltage and multiply it by the duty cycle, and that gives you the equivalent voltage. This is the way everything goes. Because what we're doing is we're turning the transistors wide open. They drop very little voltage. We turn the transistors off. They drop all the voltage, right? But there's no current flow. so the devices themselves can handle a lot of current with very little loss. We can precisely control the speed of the DC motor. We used to use SCRs. Now the predominant method is pulse width modulation. Control the speed motor. In fact, just about every PLC now comes out with has a pulse width modulated output that you can control DC motors with. Probably not with the PLC, but you could run that through a driver, right? You know, a nice big transistor block thing and drive some pretty good sized motors. So what we can do with solid state is not only can we control the direction, we can also use this to control the what? Speed. This guy right here, all we do is control the direction. Control the speed, we'd have to change the plus and minus up there. Here we can change the speed without changing the voltage up there. Because what we're doing is we're sending the motor pulses, and we increase the duty cycle, the motor sees it as a higher voltage, which means the current's going to be higher, the motor's going to run a lot faster. We slow it down. So every PLC that we have, I think the 1100 had, the 1000 doesn't have a pulse width modulation available, but the Siemens, the 1200 does, and the 1100 does. I believe to get pulse width modulations on the SLC, you'd have to buy a module. We now take PLCs, so some of y'all hadn't had PLCs, I realize that. PLCs, what are PLCs? Yeah, but what are they? They're computers, but they're specifically designed to run machines, and they program in a logic that programmers understand, not. So I highly recommend in the AUT degree, intro to PLCs is required. In the ELT, in the industrial electronics, it's one of your electives. And I'd recommend anybody take those classes. Okay, the next thing on our list is speed control. Our speed sensors. So tell me everything we need to know. Oh, another thing. What I've done, and I look back over the lab procedures that I gave out, and it's twice in those lab procedures that a circuit is not supposed to be torn down until it is checked for proper operation by the instructor. Y'all understand that? So what I've done, and I want this done before next class, inside the course content section, I have a quiz on the lab procedures. And I want everybody in the class to take that quiz before the next test. So right under lab procedures is what? Lab quiz. If we look at those lab procedures, it's in there twice. So right here, it's in here. What does this say right here? So it means if you don't give me to check it, then I'm going to let y'all buy. But from now on, if you tear a circuit down and I don't check it, if you want partial credit for the circuit, not full credit, you're going to have to do what? You're going to have to rebuild it and let me check it. Right? You understand that?
There it is.
I hope so. No, I got to check it if it operates correctly. And it's up here again too somewhere. Students of team students.
Yeah, I apologize for missing.
Well, two of the groups. We got three groups. We got three groups in this class, and two of the groups toward the circuit. Right? And it's in here twice. I'm not going to look for it. But it's in here twice that the instructor has to check the circuit before you do what? Tear it down. And I'm going to ask you questions, and that's where I ask you questions. And so when I sign that circuit off, basically I'm signing off that section of the lab, right? You understand that? And then when I come back, all I have to check is the lab question. So I'm grading the lab as we go along. But if I don't see the circuit operate, and you've got all these measurements in there, then those measurements don't mean anything unless the circuit is operating the way it's supposed to, right? And you're supposed to know the way the circuit operates. So every circuit in this class, we go over in class how they operate. Okay. This would be like me sending you off as an employer. I'm sending you off on a school on these things. I have no idea how these things work. So I send $5,000, $6,000 to send you to a school to learn how these things operate. And then you come back and you don't know how they operate, right? You come up here and you want me to tell you how they operate. So if you got any questions about the operation of a circuit, when do you need to ask them? Before the lab, when we go over in class, right? You understand? And it always bothers me where it's obvious people have no idea and they don't ask questions in class. Like what happens in a parallel circuit when you add and remove resistors. So when's that going to be done? Before what? Next class. Before you can go back to lab. So if you come back in here and you haven't done it, then you're going to have to do it before you can go to lab. Everybody understand that? So we're not going to be in lab today. So the next one on our chart as we're going to go through is speed sensors. And right now we don't have any labs on speed sensors, but we have some servo motors ordered. Yeah, this last one, this is it. This is it. No more, right? This is the 4th week of the term. We've gone over the lab procedures twice in this class. And it's the exact same lab procedures that you followed in what? Motor controls. So what different ways do you think we can sense speed? That's amazing. You can make stuff that looks like junk and it still works. So we've done position. We're going to do speed today. We haven't done weight. We haven't done force. We haven't done count. We haven't done pressure. We haven't done flow. We haven't done temperature. We're not going to do all of these. Thickness, we might talk about a little bit. Gases, liquid, motion, orientation, shape, and we already have done proximity, right? Moisture. We're not going to do viscosity. So, speed sensors. First one we'll look at is, we'll look at the two rotary encoder, a direct current, AC, and incremental encoder. We already have a good idea about the incremental encoder, right? How we can set speed off of that. So the ones that we're getting have Hall effect incremental encoders in. And they're really going to be neat. So we can use reflective light. So we can put some type of unit on here, right? And then we're using, what type of sensor would this be? Probably reflective. It's going to be a reflective sensor. Probably diffuse would probably be the most likely. And we can come up here. And one thing that they didn't cover that I'll talk about is we have a device called a stroboscope. Have you ever seen a strobe? Y'all know what a strobe does? They used to be very popular in disco. Well, they had them strobe lights up there and make everybody look like they'd be moving, but it flashing, they'd be in a certain motion. It made everybody look like they were really jerking. Well, if we can get a strobe light and we can start shooting it at something that's in movement, right? You understand? And then we turn it until it becomes it appears to be what? Stationary. Anybody ever use a timing light on low car?
Yes.
We were out when we was in the Navy. So what a strobe light would do is the motor was sitting there spinning, but on the crankshaft that came out, they had a mark on there. And then they had some measurements beside it. and you'd put the strobe light and you'd park it in that mark, and that's the way you set your timing. So you'd look at your data, and it would say you want to set it 2 degrees before top dead center or something like that. Well, you do it with a strobe light. So you come up here and you point it down there, and you take the distributor and you realign the distributor until they did what? Until it lined up. Now the firing angle is set electronically. So it takes a little while to fire a spark plug. So what you want to do is you want to fire it right before it, while it's still coming up, right? You understand? You tell the spark plug to fire because you want it to fire when it's supposed to go what? Down. But if you fired it up here, it would already be moving down before you did what? You fired the plug. So normally what they do is they fire it right before it gets to the top, and they call it top dead center. So what we can do with a strobe tach is we can actually we pulse it, we change the frequency until the rotor looks like it's stationary. And if the rotor looks like it's stationary, it means that the light is doing what? Flashing at exactly the same speed as the motor's turning. If you see two things, it means you're going twice as fast. So we can use stroboscopes to measure speed. I think Nancy has a stroboscope on hers. What's real neat is you just take it and you point it at it, and then it gives you that reflection back. But this is one way that we can measure speed using a diffuse photoelectric, right? Everybody okay there? This is a variable reluctance. We've already looked at this. So how does this guy here work? Yeah, these guys are still used. Anybody know where they're used? The major use of variable electric systems. Used to, when you was flying down on your car, you slammed on your brake, you slammed on real hard, they would lock up. Then they came out with a circuit for airplanes they called an anti-lock system, so the planes wouldn't do what? They don't lock up. So what would happen? So what did you learn? Anybody remember how to do what to do when you're trying to hit the brakes real hard? You're supposed to pump them real fast. And then what happens is your wheel does that, and it has a better tendency to grab and start sliding. Well, they figured out, of course, how to do that electronically, but they got to know the speed of the sensor of the wheels. They got to know when the car is still in motion and what, and the wheels are locked. And they use variable reluctance sensors. So variable reluctance is probably the most widely used a lot in industry. So they're very rugged. They can be run in very, very harsh environments. But what this does, this deals with the strength of the magnetic field. We're not changing the number of wires, but what happens every time one of these blades go by that magnet, the magnet concentrates into that what? Concentrates into that thing, which causes, I said, don't change it. It changes the motion, right? You understand? So every time that blade comes by, the magnetic field concentrates, which causes the magnetic to do what? Pulse, which gives us a pulse of it. These guys are very rugged. They're used in extremely harsh environments. And the one we have on the test would be the same. So how many blades does this guy have? Oh yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. This guy here is 35. So this guy would have a better resolution than the 4, right? You understand? As far as sensing speed and also as far as sensing position. Now, the biggest problem we have with these guys, they work real well at speed, but at high speeds, but they work very poor at low speed. Because the slower it goes, the less concentration you get, right? You understand that? So, I've seen these used on a lot of motors. We used to have a set here. We had a servo system put out by Seco in one of our labs. I'm not going to talk about that. We had a guy that came in, and I will talk about that. I'm not going to give you his name. We had a guy that came in and was over our program, and he had no technical skill at all. He was a PR guy. So he wanted things that looked good. So we came in here. I came in here one Saturday, and he was in this lab, and he had a couple of guys throwing stuff out that window. into a big hopper down there, and he was throwing away everything that looked old, that didn't look good. So our Seco drives got thrown away.
Where did he find his next job?
Well, unfortunately, they kept him around here for a while, but he finally moved up to,
That was a joke, I really don't know.
he moved on. He went to another college, but from what I understand, they got rid of him there too. So variable relatives are very, very solid. They look a lot, but the surface will be metal up here. They're basically, this guy would be shielded, right? So all you got to do is have a metal wheel that spins. It could be coming from a transmission, but I think these for your auto brake systems, I think they're are your anti-slip. Is that what they call them? Anti-slip systems, which most cars have on them. And you can tell sometimes. Have you ever did that? Like coming off the interstate or something, you hit your brake and you see your car. This is Hall effect. This is what we're getting. Ours is not quite like this. But this works almost exactly. This one works almost exactly like the one that's on the last power plant. So what we do is we have a magnet inside the sensor, and then we have the Hall effect, and then we have just a gear that's got a bunch of metal. And then every time the metal teeth comes around, it concentrates the magnetic field through the Hall effect. So the Hall effect is not sensing the metal. The Hall effect is sensing the change in the magnetic field. And then this right here would give us a pulse for every one of those things. Now the one we got has got two sets of blades on there. It's got two Hall effect sensors, and they're all set by 90 degrees. So ours would be called a quadrature encoder, right? Are we okay? Yes, I forgot where I got this at. The encoders can be magnetic, so the actual encoders themselves, I think the one we're getting doesn't have the magnet. The actual encoder itself is magnetic. I think that's what it was. It's got 64 blades. Then it runs to a gearbox that I think it's 385.5 to 1. It's over, I think, 8,000 pulses per revolution. A quadrature encoder has a second encoder wheel offset by 90 degrees. Then this would be a quadrature encoder. So that's why I put this in there. So the servo motors that we're getting has a quadrature encoder. It's all of that. Next thing we have is DC generators have been used for years as tachometers, or something called these tach generators for short. We do that used a lot. So what determines the amount of, so these guys spin permanent magnets because we don't want the magnetic field changing. So what would determine how much voltage we get out of these things? So what determines the amount? Strength of the magnetic field, which we're not changing. The number of conductor loops, we're not changing. So what's going to determine the amount we get out here would be the speed of the motion. So I've set up a little MG set. You know what an MG set is? No? Motor generator. And I don't have my voltmeter. I need to get it out. So what we have here is we could run this either way. What's nice about a DC motor is that it can usually be DC motors can also be used as generators. So what I have here is this is heat shrink, so this does a lot better, and they have the same size shaft. The problem I had on the other one is the shaft on the pot was real big and the shaft on the motor was real small. So this is the way I have this connected. And of course what happens, you can run this motor in DC. It don't matter which one I use. I think this is Anybody got their voltmeter? I had it hooked up to an encoder. Somebody got one that's got alligator clips on it? That's okay, I can get some. Fine. So what we're going to do is we're going to look at the output of our tachometer. And I did have a circuit, guys, that would control the speed. It was almost the same. It was a lot like the last circuit. So we got it on volts DC. Of course, I just got my meter hooked up. And of course, as we turn it down, what happens to the output of my tach generator? Going what? Can you see it? Going down. When I hear the motor stop. Come up here, it's turning now. But what I'd have to do is I'd run it at its rated speed. I don't know what this motor's rated at. I think 15 volts. And that would be my output, 10 volts, right? And then that would be my transfer function. But what I'd have to do before I got a transfer function is I would have to measure the speed of this motor at that voltage. If I can measure the speed of that voltage of the motor when my tach generator was putting out that voltage, then now we can make that voltage relative to speed, right? So I'd have to have some means to measure the speed, the actual speed. So that's about right. That's about 10 volts out of the generator when it's running at almost 15. And this is directly proportional. I mean, it is really linear. So I could take this and I could run it into a controller. I could run it into an analog to digital converter. And that way I could run it into a computer, right? Well, these are still used a lot, not much on newer applications, but these were the primary method of closed-loop speed control of motors. This could be AC or it could be DC. DC motors, AC motors. The tach generator itself could be an AC or DC tach. This is what would be considered a DC tach. Are we okay? Any questions on there? So this is not a servo motor. This is a motor, and I had to literally attach a speed sensor onto the motor. Now, if you take the speed sensor and go to a gearbox, then you're going to have to know the ratio of the gearbox, right? You understand that? Yes or no? Huh? Everybody understand that? Okay, Eric? Well, we can do two things with gears. What's the two things we can do with a gear? But yes and no. So if we step up, if we use them to step up speed, we lose torque. If we use them to step down speed, we gain torque. So we can either use them as torque multipliers or we can use them as speed multipliers. And it's the ratio of the gears. So you can count the number of teeth on your gears and then take the output gear divided by the input gear. Gain is always out over in, right? You understand that? Or you can take the diameter of the gear. The diameter of the gears, it would be your output diameter over your input diameter. Everybody understand that? Once you calculate that, then what we're going through here, this guy right here has It has 1, 2, 3, 4, 5, 6. Let me count it. 1, 2, 3, 4, 5, 6 blades on the encoder. But it goes to a 65.5 to 1 gear ratio over here. Now this is where I'm trying to set the speed, right? You understand? It's over here. This is my working right here. Okay, so what would this output see that encoder as? How many blades would it see it as? There's 6 on this end, right? But I'm going through a gear ratio of 65.5 to 1. So what would it see? What would this end see this encoder as? How many blades? Huh? There's 6 back here. But this guy has got to turn 65.5 times to make this guy over here turn what? Once. So this guy sees this 6 times 65.5. And that's what you got to know. You got to know what this sees the encoder as, not what the encoder is right there. Because this is where we're trying to set the speed at, right? You understand? This is the output shaft right here. And then if you take this and run it through a set of chain drives, which is what this robot did, you'd have to know the ratio of the chain drives, and you'd have to figure out the entire transfer function to figure out how fast the robot moved, right? You understand that? So let's just stop right here. So 65.5, that's the ratio to 1. Most of the time it'll be to 1. This has 6 blades on it. What does this see? So how many times would this thing right here pulse for this guy right here to turn 1 revolution? Get your calculators out and figure it for me. I can't do that in my head. What are y'all going to do? 65 times 6. 65.5 times 6. You can't leave off the 0.5, right? 393. So this guy sees this guy as what? 393 pulses per revolution. So you're going to have to figure out the transfer function on these encoders on what they go through. That makes sense. The ones we're getting has a gear ratio of like 385 something, and it's got 64 encoder blades. So it's like 84,000 or something like that. So what we're doing here is we're using an encoder. Now you can use either one. You can use either one of these to sense speed. You wouldn't use both of them to sense speed, right? You understand? So this is a quadrature encoder. And what's the advantage of a quadrature encoder? What does it give us? In speed. So not only we can get 3 things out of a quadrature encoder. I think you said it one. We can get what? Speed, direction, and position. On an incremental encoder, the only thing we can get is position and speed. Everybody make sense? And encoders they can be magnetic, they can be optical, they can be Hall effect, which would also be a variable reluctance in Hall effect uses the principle of magnetics, right? You understand that? And then of course your optical depends on they're through the beam too. No, a tachometer is a tachometer. A tachometer is a term usually used to indicate is a generator. It usually gives you a voltage proportional. But technically every one of these can be considered tachometers. Because what is tach? In mechanics, what is tach? So anybody have a tachometer on their car? Some cars put it on there even though they're automatics. My car's got one. Basically means nothing. That's not true. If you shift it. But what's it measuring? 1,700 RPM. What's it measuring? revolutions per minute, but it's the RPM of your motor, right? So tachometers measure speed. They measure speed. That's what they do. Tachometers measure speed. So technically, any of these things I'm talking about, a speed sensor could be technically called a what? Tachometer. It's just usually we call these tach generators because they generate a voltage proportional to their speed, right? You understand? And then we have optical tachometers, which would be the ones that we're fixing to do. So, okay. Okay, let's go ahead and take a break, another break. Well, Melvin goes to sleep over here. I see my wife going.
Somebody keep that. Granddaughter